I'm just going to do sound speed just in case. Okay, awesome. So I'm Deepto. I'm here in the flesh now. Actually, can I get your names? No, I know Josh and Lily and
Bishop.
Bishop. Okay. Awesome. So today I wanted to talk about the concepts of symmetries and groups. I think it's helpful if you have the prior knowledge from the other videos I posted, but if not, that's fine. So to kind of quickly go over that, I'm just going to talk about some notation I'm going to be using and some basic concepts. So in my videos, the whole topic was about logic, sets, and functions, and primarily we're talking about sets. And sets are these, thank you, these objects which serve as collections of elements. And elements are just some arbitrary thing that we can consider. So you're probably familiar with sets as being collections of numbers, but it doesn't have to be that. It can be literally anything. And so if we want to talk about something, let's call X, being in a set, we call it S, and we use this sort of E looking symbol. So this we read as X is in S, or X in S. So we're saying X is an element of S in this case. If we want to talk about all the elements of the set S, we use this symbol. This means for all X in S, or for every or for each. If we want to say that there exists a certain element of S that satisfies some property, then we use this backwards E, say there exists an X in S, and then such that something, something, something. Right, so for what I want to talk about today, the next thing would be functions. So functions are a way of making associations between elements of two different sets. So you should be familiar with the idea of a function having a domain and a range. The domain is where the inputs come from, and the range is where the outputs live. So if we had a function whose domain was a set called A, and its range was a set called B, we would denote that as this, which is probably a bit new to you, but I think you'll get used to it after a while. And what's happening is that this function takes in an element of the domain and then maps it to an element of the range. So we'll call that little b. So we can have this visual idea of this being the set A, this is the set B, and this little a is an element of this, and then what the function does is associates it to this point, which is little b. It'll do this for every element of the domain. Okay? Then an important idea from there is when we can do this in reverse. So our function f tells us how to take elements of the domain and then map them to the range. But what's often really important is being able to do exactly the opposite of that. So if we know our value of a function, so there's a particular value of the function f, we want a way to be able to go back to the element of the domain where it came from. So f would go this way. We want a sort of inverse mapping that goes that way. Okay. And when I say that, what I mean is that we want this to exist without any problems. So the problems that could exist, let's say this is the original function f right now. We could have a different element of the domain, let's call it a prime. And this could also map to b. What if we try to go backwards? So if you want to answer this question? If we were to go backwards, where would we go to?
You could only get one of those pieces of the set A.
Right,
likely.
but the problem is both of them map to here, right?
Mm-hmm.
So there isn't really a clear answer. You could say that you go to both of them, but then it's not really a well-defined map, right? It has what we call multi-valueness. It is something you don't like. When you were in middle school or junior high, or whenever you learned it, you learned about something called the vertical line test. And you put this vertical line in a graph, and then if it intersected 2 points on the graph, you're like, no, not good. And this is the same thing, actually, in terms of going backwards, because it has one input and then 2 outputs. We don't like that.
Wouldn't a horizontal line also be necessary if thinking of it in that 7th grade mindset?
Yeah, exactly.
Okay.
So that is really important connection. So in terms of going forwards, we have 2 inputs that map to the same 1 output. So in terms of a traditional graph, if you have some function like this, then yeah, if you put a horizontal line, these will have the same values because it's on the y-axis, but you have different inputs. So if you want to go back from just this value, you wouldn't know where to go to because you have 2 different inputs. So yeah, when we're talking about wanting a function to have a sensible way of going back, you want it to pass the horizontal line test. Okay, so that's something that would be bad. Another thing that would be bad is if there was an element of the range that was not a value of f at all, because then it just has nowhere to go back to. So these are the 2 things we want for a function f to be what we call invertible. And the mental idea is that, let me change this around a bit. A prime, if it's different from A, it must always have a different value. And then, if we could draw it out, every element of this set would be filled up by these mappings. Okay, so why is that important? It's important because invertible functions, we'll see, will give us a way to define a notion of equivalence between 2 sets in certain ways. And if you want that notion of equivalence to be through this function, and you don't have a way to go back, it's kind of like you're saying A is equal to B, but B is not equal to A, which doesn't sound right. So that's why something like that is important. And we'll see that in a few minutes, actually. Okay. So, do you want me to leave this up, or should I just erase it?
It's slidable, so
Yeah,
if you
I
just
know,
wanna
but
push it over.
like,
I think we're good. Yeah.
It makes sense.
okay. So should I? Okay, I'll get rid of it. Okay, cool. So today we're talking about symmetry. And so I want to ask you, when I say the word symmetry, what do you think of?
Equal on both sides.
On both sides. Okay, so you're thinking of something like, okay, let's say we have like a square, and then we put a line through here. On both sides, it looks the same. Okay. Have you heard of the concept of rotational symmetry?
Mm-hmm.
Okay, so what would you use to describe that then? It's not exactly the same as this, right? But it's still kind of connected.
Yeah. You get the same projection if you rotate it a given number of n angles, or n degrees.
Yeah. So let's say we had an equilateral triangle. Kind of good. If we rotate it about the center 120 degrees or 240 degrees or 360 degrees, it would end up looking the same, right? So these two are actually connected. It's the same idea. If we reflect the square about this line, then we produce the same shape. Okay? So in both cases, we're doing some transformations to the shapes here, and it's preserving something about it that leads us to say that it ends up being the same. Okay? So I brought in some examples. So here I have a Rubik's Cube. So this is a cube, and then there's a tetrahedron there, regular tetrahedron, and then regular dodecahedron. So if you just play around with it for a bit, you can see that ignoring the colors, if you just look at it, you can do a bunch of transformations that preserve the shape of this thing. So with the cube, I can do a bunch of these rotations. I can do what are effectively reflections. So here, if I turn around like this is like a reflection. And I can do a whole lot of things with this, right? And at the end of it, it will still end up looking the same with the same orientation. Okay. So we can then actually generalize this concept of what a symmetry is. So from here, we're seeing that a symmetry is some sort of transformation that leaves something about this object invariant. Right? So symmetry transformations preserve some property of the object that's being transformed. Okay. The idea is that when we transform the square, let's say, when we reflect it, it's not literally the same. And we can see that because if we label these points 1, 2, 3, 4, and then do the reflection, we end up getting a square, but the points will be 4, 1, 3, 2. Does that make sense? Okay, so we've actually done something to the square, but something about it is the same. And so, namely, the shape is the same, right? But also the sort of orientation, or the connections between the specific points. So originally we had 1 was adjacent to 2 and adjacent to 4. And a symmetry for the square will preserve that. So 1 is again adjacent to 2 and adjacent to 4. Otherwise, we're kind of messing with the geometry of it. So they're not literally equivalent, but to some extent they are equivalent. And that extent to which they're equivalent tells us what the kind of symmetry that transformation is. Okay? So one thing to note that I said before with invertible functions is that, I had this concept of an invertible function can tell us when certain things are equivalent. And that's because we can go back, right? And so with symmetry, our fundamental concept is that if two things are related by a symmetry transformation, there's this notion of equivalence. So in order to actually confer that idea of equivalence, any symmetry transformation should be invertible. So with this example, if you reflect the square like this, to invert it, you would just reflect it again. And you'd get back to the same thing. Or if you rotate this triangle, so let's say it's 1, 2, 3. Okay, we get a triangle that looks like this. To invert this, we would just rotate the opposite direction. Okay. So,
can I ask a question?
Yeah. Oh, if you want to ask questions, just literally blurt it out. I don't care. I already know this stuff, so just don't let me keep talking.
So are symmetry transformations specific or general? Like, for instance, if you take the root of x squared and you apply that to the normal numbers, or the natural numbers, it'll be a symmetrical transformation. But if you apply it to all real integers, you get an asymmetrical transformation. So is that just a
What do you mean by asymmetrical?
Like, if you apply the root of x squared to all real integers, right?
Mm-hmm.
-1 is transformed into 1, and you can't take that back to all real integers.
So when you're talking strictly about positive numbers, the idea of the square root is literally the inverse function of x squared. Because the idea is that you get back to literally where it came from, right? So this is true if x is positive. And so this kind of function is what we would call the identity function. Okay. So the point of an inverse function is that you do the function and then the inverse function, you get the identity function.
Mm-hmm.
That's the kind of idea of undoing it. For negative numbers, what's happening is that this is basically the horizontal line test. If you have x squared, then you do this horizontal line, it fails it, right? So in the videos I talk about this concept of injectivity, which is basically not failing the horizontal line test. But x squared does. And so what happens then is that x squared doesn't actually have an inverse function.
Mm-hmm.
And so what you have to do in some cases, which is what you do with this square root function, is that you cut out some part of the domain so that the function is now injective. And then you also have to cut out some part of the range to make it map to everywhere. And then you can define an inverse function. So that's what's going on there.
Mm-hmm.
So, for example, you were talking about a negative number squares to a positive number, and then the square root is positive. The square root being positive is just an arbitrary choice that we make.
Mm-hmm.
But you're right that if you want to do it for all the real numbers, it's not going to work.
Sure. So would you, if you restricted the domain and range just to only the first quadrant, would you be able to label that a symmetrical transformation even though it's restricted?
Yeah, and it's not just a symmetry transformation, it is an identity transformation.
Mm-hmm.
Because you're transforming x to x squared and then back to x.
Mm-hmm.
So at the end of the transformation, for all x, you just haven't changed it. So it's even a more special case of the identity, of a symmetry transformation. Okay, does that make sense?
Mm-hmm.
All right. So I think that's actually what I was going to talk about. So, yeah, I wanted to talk about the identity transformation. So, yeah, I'll go with this. The identity transformation on an object just doesn't change anything. So we're thinking about this object as a collection of points. They have certain connections with each other. And the identity transformation just leaves everything the same. So we call this I. And then all these points are still the same. And the point is that if you do literally nothing, then any property that this has, this should also have, because they're the same thing. If that were not true, then you can't really call it a property of this thing, because then it doesn't have a well-defined value for that property. Okay, so what could that be? It could be like the area of the triangle. You do the identity transformation, it should have the same area. Hopefully. Right. So, therefore, we can say that the identity transformation is going to be a symmetry transformation. So, abstractly, I've said any property of whatever object you're transforming will be preserved under the identity transformation. Okay. So, where should I put this? Move this way. Keep this. This is important. Okay. What's hopefully also clear is that if you have a symmetry transformation, say like this, under the symmetry transformation, some property is preserved. So here's the shape and the connections. And because that property is the same here as it is here, when we go through the inverse transformation, the same thing happens. The property of this shape is the same as this shape. So that property is preserved through the inverse transformation. Okay. So the inverse transformation of a symmetry transformation is also a symmetry transformation. All right, let me label these actually. Okay, does that make sense? And so with like these shapes, it's like I could rotate it like this. That's a symmetry transformation, and therefore, if I go back, also symmetry transformation. And for similar reasons, if I were to do multiple symmetry transformations and like compounding them, then the property should still be preserved. So I have 1, 2, 3. Maybe I rotate this 120 degrees. So this is 1, 2, 3. And then I could reflect this about y-axis. So that gives me 3, 2, 1. And if I do this, and it doesn't matter how many I do, if each one is a symmetry transformation, then all the properties that we care about, this property will be preserved, so it changes to the same thing. It doesn't change. And then for here, it also doesn't change. So in the end, the property doesn't change. Okay? So compounding, or what we're going to call composing, symmetry transformations produces another symmetry transformation. Okay? So let me bring up some more examples before I go into more abstraction. So I've been talking about some geometrical stuff, but this is supposed to be important to physics, right? So maybe let's do some physics. You're all in MEM?
Yeah.
Okay, so you should be pretty familiar with something where symmetry is important. I don't know, maybe you can guess what that is right now. Okay. Okay, if you can't, the answer is Gauss's law. So, with Gauss's law, what you're doing is you're taking a system with some sort of symmetric or symmetrical charge distribution. You're exploiting that symmetry to make the integration in Gauss's law very easy, and then solve for the electric field. So, for example, if you have some spherical charge distribution, you could think of it as a sphere with uniform charge. If you want to write that out of pi radical 13, you can. It was decent, actually. And what you do here is you take a Gaussian surface that's a sphere, you compute the enclosed charge in here, and then divide it by 4 pi r squared E naught, and that gives you the electric field, right? Okay, we're not going to actually do that problem. The point here is the symmetry. So how exactly can we apply this concept of symmetry transformations to this setup to see that there is this spherical symmetry here? Well, the idea is that if we have the center of the sphere here, if we rotate the whole universe, but mainly this sphere, in some way, the charge distribution will look exactly the same as it did before. So I can do some kind of rotation about some axis, That's supposed to pass through that. And then that rotation will give the same charge distribution. What's the significance of that? Well, the charge distribution determines the electric field, and it determines the electric potential. It determines all of the physical things and all the physical fields that are produced as a result of this system. So if the charge distribution has this rotational symmetry, then so will all of the physical quantities associated with it. So for the electric field, what that means is that if you have an electric field like this, and you now rotated your whole system, you're also going to rotate this electric field vector. So, okay, I didn't choose a very good rotation for this. Let's imagine we're rotating this way. And this rotates to here. Then this should match whatever electric field vector there was before the rotation, because everything should be exactly the same under the rotation. Okay? For the electric potential, it's a lot simpler. It just has the same value if you rotate it. All right? So, how much time do I have? I think I have more time than I expected. Maybe let's talk about another example. This will talk about more of the mathematical sort of ideas that we'll use. So we could talk about a physical body in space. So I'm going to call this B. And we can deform this in some way, or just, not necessarily deform, but just transform it, move it in space in some way. By a function, I'm going to call it phi. This is the Greek letter phi. You might have seen a different version of it, but this is also valid. This can become some other objects. I'll call it B prime. And something we might care about are the distances between 2 points in the body. So maybe these 2 points map through this function phi to here. And something that we might care about is if the distances are the exact same. All right, if for every pair of points in the body, the distances are the same before and after. All right, so we could have something like a distance function. So I'm going to use some notation that maybe you're not familiar with. What this distance function does, it takes in a pair of 3D points. Okay, so the R3 is talking about 3D space. The cross means we're taking ordered pairs of elements in these two things. So those are our inputs, and then what it spits out is a positive real number. So it's R for real, and then plus for positive. Okay? So, actually, I don't know if the camera can see that down there, but...
You can.
Yeah, you're
Okay,
good.
cool. If we want to say the distance between points is preserved under this transformation, so qualitatively we're saying the distance in B prime is equal to the distance in B. How do we do that mathematically? Well, we're saying that this is true for all pairs of points in our body. So we want to start out by saying for all x, y in the original body, what is the distance in B prime? So we want to find out what the distance between these 2 points are, right? So let's say in the original body it's x and y. Here, this is the result of this transformation. So this point would be 5x, this would be 5y. The distance between these two would then be the distance between 5x and 5y. Okay, these are the two inputs. That's what this is. And in here, it would just be the distance between x and y. Are there any questions about that? Okay, cool. So this is a pretty common setup for what we're going to see going forward. We have just some function. So actually that function would be phi. And then there's this sort of property that's, in this case, is the distance function d that is being preserved once you actually transform these elements x and y. Okay? So how we could also say this, because we're going to say that we can invert phi, is that for all the elements in the new body, called x prime and y prime, that the distance between x prime and y prime, which is again this distance in b prime, is equal to the distance between phi inverse. So this is what I should have mentioned that before, but this is what we use to denote the inverse map. Phi inverse of x prime and phi inverse of y prime. Okay? All right. So this sort of transformation that does preserve the distances is what we call an isometry. And specifically we call it an isometry of this thing B. And something we could say is that B is isometric to B prime, or B prime is isometric to B. And we could write that as this. So the idea is that these two things should mean exactly the same thing. Okay. Does this seem kind of new to you? Yes, nodding head.
Somewhat.
Yeah? Okay. This is actually something that you've done probably a while ago. So whenever you're talking about congruent triangles or congruent quadrilaterals or anything like that, we're saying, you know, the side lengths are the same, the angles are the same. What you're talking about are two different shapes upon which you can do a transformation to one to get to the other, and the distances are preserved. And when you're talking about this shape is congruent to this shape, you're saying that those two shapes are isometric to each other, that there exists an isometry between them. Okay, I saw one of you had a moment of great understanding, so that makes me pretty happy.
It all connected.
Yeah. So hopefully you can see that these kinds of concepts, they're really abundant in math. And you talk about in high school geometry. We're going to see that you've talked about them in like algebra. You talk about exponential functions. And so what we want to do is then generalize this concept in a more abstract way. Okay, I do have time for this. Good. Oh, wait, what do I need? I need this. So maybe, where'd the eraser go? Oh. Oh, there was actually one thing I wanted to say before I move on to this abstraction. So the things that we're preserving under the symmetry transformation the sort of thing we're intending to preserve, we could call like the principal invariant. So in general, if something is the same under a symmetry transformation, we could say it's in an invariant of the symmetry. For isometries, we could say the main thing we're preserving is the distance. We would call that the principal invariant. And then other things are just other invariants of the symmetry that are consequent. Okay. So these were important properties of symmetry transformations. And we can encode them into a more abstract algebraic context through the following. So let's say we have a set G with an operation that we'll denote with a dot. And this dot is a function that takes in pairs of elements of G. So the cross, again, that's how we denote we're taking an ordered pair. And it spits out elements of G. So a pretty simple example would be literally multiplication. So if we think about multiplying real numbers, this would be R cross R is our domain. We take in pairs of real numbers, 3 times 4, and it spits out a real number that's equal to 12. Pretty much? Okay. Okay, so with symmetry transformations, our set G is the set of symmetry transformations. The operation between them is going to be composition, so compounding these transformations to produce more transformations. Okay? If you were to be literal about how to write this function, it would look something like this. This looks very stupid. So we define this as G1 and then dot G2. Okay, so there are some rules that we can say to reflect these properties. So one thing that I didn't mention is that the composition of these transformations is associative. So that basically means I can do, if I have 3 transformations, I could do this, then this, or I could do this, then this, and then the last one. Obviously, you can see that it wouldn't matter, because you get the same result. Okay, what that looks like abstractly, if you take any 3 elements of the set G, and you do this operation, you would have something that looks like this. So we would do this one first and then do the whole thing. Or we could do this. But in the end, it doesn't matter.
So just to confirm, is this for any operation represented by the dot, or are these dot operations only symmetrical?
What do you mean by symmetrical? Like they represent?
As in, like, does the associative property that you're discussing only pertain to certain operations represented by the dot?
No. So what we're doing here is we're generalizing this to an abstract context. So you could consider any set and then try to construct an operation on that set. So you take in 2 elements and then spit out 1 element, and then potentially it could satisfy this property.
Okay.
But it doesn't have to. This is a condition that we're imposing.
Okay. Thank you. That
Okay.
makes more sense now.
Good. So, right. This is kind of the least interesting part of this.
Mm-hmm.
But the more interesting ones, let me just, is this. If we have, not that. Sorry, this is actually encoded in this. because when we're doing the operation of, so with symmetry transformations, it gives something that is also a symmetry transformation. So what did I want to say? Oh yeah, this. So for all elements of the set G, there exists, wait, no, I want to do this the other way around. Sorry. There exists something that we'll call 1 in the set G, such that for all elements of G, 1, I'll just call this times for, it's easier to say. 1 times G equals G times 1, which is equal to G. Okay? This is like the identity transformation, because I can do nothing and then something, or I can do something and then nothing, and I get the same thing at the end. And it's always that other transformation. Okay. And then every element is going to have an inverse with this operation. So for all elements of G, there exists this G inverse in G, such that G times G inverse equals G inverse times G, which is equal to our 1, which is this 1, which we call the identity element. Okay, so let's say this is one property, it's another, it's the other. One thing I want to point out, this operation is not necessarily commutative. In fact, it's really important that it's not. Because if you look at something like this, I hope I get this right. Right now, showing this to you, it's white here, green, orange, blue, red. Okay, so remember that, because I'll probably forget. So if I rotate this way and then this way, so I have blue and then orange, yellow, white. Okay. I'm probably going to forget that. This is what we had originally, right? Please say yes. So then if I did it the other way around, I would go like this. Yes?
Mm-hmm.
Okay, this is different from what I had before, right? Because I had orange and then white on top. Okay. The point is that 3D rotations do not commute. So that should be somewhat interesting because you're used to operations that do commute, like addition, multiplication, all of that. You could say subtraction, but subtraction is really addition, so it is commutative. The consequences of rotations not commuting actually go down to quantum mechanics. And it gives you this idea of what we call a commutator algebra or Lie algebra of angular momentum operators. It's actually also important in classical physics for talking about rotations generating angular momentum generating certain transformations of quantities and seeing how it produces changes in a quantity under rotation. So going back to this, these 3 statements are the axioms of a group. So group is this abstract mathematical concept that we could talk about just in this abstract landscape. But what's really important to us in physics is the fact that it encodes all of these properties of symmetry transformations that we want. And if you do go through all of this abstract work with groups, you'll see in the end that it gives a lot of payoffs in terms of talking about symmetry transformations. Okay? So, in particular, when we're talking about the set of symmetry transformations in some particular context, we call that a symmetry group. And what's often super important is either describing what the symmetry group of something is purely mathematically, or making connections between a physical symmetry group and a mathematical symmetry group that you didn't realize was related at all. So for example, if you could just toss me that one. Okay, so if you were looking at this, you probably saw that I had written numbers on it, which seems a bit mysterious. So why I was doing that? Well, about 2 years ago, I had my final exam in a group theory class. And one of the problems was asking to show that the group of rotational symmetries of a regular dodecahedron. So I'll call this a megaminx because that's what this thing is called to Rubik's Cube people. Is what we call isomorphic to the group A5. So isomorphic means that this group is equivalent to this group in the sense of groups. So the algebraic structure, the details of this operation, they're exactly the same. All that's different is what you call the specific things, the elements. Now, what is A5? I'm not going to go to it in detail, but A5 is a set that talks about the set of permutations of 5 objects. Okay? This is not an easy thing to show. I think we were lucky because COVID had just started, and so we got to use textbooks. It was like an open book exam. But yeah, it's something that's not easy to show. The next thing was talking about finding a non-trivial homomorphism between A5 and S, or not that. A homomorphism between A5 and S6. S6 is talking about the permutations of 6 objects. And yeah, I'm not going to go into it in detail, but I'll talk about how you can maybe make a connection to this. If you look at this and see why I put numbers on this, you might have noticed, or maybe not, but I put the same number on opposite faces. So there are 12 faces to this thing, but there are 6 pairs of faces. And whenever you rotate it, because the faces are originally exactly parallel, they'll always stay parallel under rotation. So you could break this dodecahedron down into 6 pairs of faces, or how I thought about it was 6 kind of axes that connected these faces. What a rotation is doing then is it's permuting all of these axes and just shuffling them around when you do that. So you can understand these rotational symmetries of the dodecahedron as acting on a set of the 6 axes. And then because this is the same as that, there's this connection. Okay, so something that I think is cool about group theory from my exam, I wanted to share that with you. That is probably going to be the end of this lecture. I think tomorrow we'll talk about more abstract stuff with groups, certain properties that we want, so homomorphisms and isomorphisms. And then that will pay off for us later when we talk about symmetries in classical mechanics and quantum mechanics. All right, awesome. Thanks for coming out.
Thank you.